Okay, think about that feeling, total frustration when the power clicks off. Now imagine you're the one trying to keep the lights on for like a whole city. It's this constant fight against uh, unpredictable problems in the system. And with everything changing so fast in energy, that fight's getting even harder. Today we're diving into some new research, and honestly, it looks like a really revolutionary way to, well, win that fight more often.
That's right. Our mission today is taking a deep dive into this really interesting new paper. It's all about finding the best spots for switches, specifically in these interconnected microgrids. And like you said, it's not just some minor technical thing. It's aiming for power that's, more reliable and actually more affordable for all of us.
Okay, let's unpack this a bit. So for ages, right, the big challenge for power companies has been keeping things running smoothly, even when stuff goes wrong, a tree falls in a line, that kind of thing, unavoidable faults. And operators have used these things called remote-controlled switches, RCSs, to isolate the problem spot and get power back quickly. There's a process, FLASR, fault location isolation and service restoration. That's been the standard for decades. But you mentioned things are changing fast. So where does this new research really shake things up?
Well, the whole game has changed fundamentally with microgrids popping up everywhere and distributed generation. Think rooftop solar panels, local wind turbines, things like that. This introduces something called bidirectional tower flow, which sounds technical, but basically, traditionally, power just flowed one way, right? Big plant to your house, simple. But now with local generation, power can actually flow backwards onto the grid sometimes. And that makes it incredibly tricky to figure out where a fault is and how to reroute power effectively. So what's groundbreaking here is that this research offers the first solution, really, for placing switches optimally when you have a whole network of these interconnected microgrids. It tackles that complexity head on.
Okay, so they figured out something that was a real sticking point before. But bring it back to the listener, right? What does this actually mean for you, for your power bill? How does this new method improve things day to day?
Yeah, what's really cool, I think, is how efficient this new approach is. It's graph-based. So instead of calculating the potential outage time for every single load point, every house, every business individually, they found a way to group them. They call them paths of common nodes, or POCNs. Basically, all the points on one path experience the same interruption if there's a fault affecting that path.
Okay.
So it's like finding a shortcut for a whole neighborhood instead of checking every single address one by one. And the smart grouping, it reduces the calculation time, the runtime, by about 20%.
20%.
Yeah, roughly 20%, which isn't trivial. It means operators can figure out the fix much, much faster, potentially stopping bigger issues before they really impact people.
Huh. So it's like creating a much smarter, faster GPS for electricity, basically. Cutting down the time needed to reroute around a problem. How does that speed actually translate into, keeping the lights on more reliably?
Well, the simulations they ran show some pretty impressive results. For example, they looked at SAIDI, that's the System Average Interruption Duration Index. It measures how long, on average, a customer is without power each year.
Right, the Q metric.
Exactly. And in one case study, SAIDI dropped dramatically. It went from 1.7 hours per customer per year, which was the baseline, down to just 0.65 hours in their best optimized scenario.
Wow, less than an hour a year on average.
Yeah, think about that difference. It's huge. It potentially cuts the overall system unavailability down to about a third of what it was.
And, okay, better reliability is great, but there's got to be a money angle too, right? Less downtime must mean lower costs somewhere.
Absolutely, no question. Better reliability directly cuts down on what they call customer interruption costs. It's expensive when the power goes out for businesses, for everyone. The research showed that just by properly considering how these microgrids connect, one case study saw operational costs drop by 21% just from interconnection. Then, when they also factored in those distributed generators like solar within that connected system, the cost reduction hit 27%.
27%. That's significant.
It really is. It's because having these interconnected grids and local generation provides more backup routes, alternative supply paths. So if one line fails, power can often be rerouted from another direction, keeping more people online and reducing those costly, unrestorable situations.
And crucially, this isn't just a theoretical model that works on paper. You mentioned simulations, but they tested it on larger systems too.
That's right. They applied it successfully to the modified IE123 node test system, which sounds technical, but it's basically a well-known industry standard benchmark representing a decent-sized, realistic distribution network. So yeah, proving it works on that scale shows it has real-world potential. It's not just for tiny lab models.
Okay, so this deep dive really seems to show that thinking smarter about switch placement, especially with interconnected microgrids and local generation, it isn't just some, abstract engineering exercise. It's a concrete way to get more reliable power, potentially cheaper power, and build a grid that's just, well, tougher, more resilient.
Exactly. And it leaves you with a pretty big question to think about, doesn't it? If we get really good at optimizing these local interconnected microgrids, could that eventually make massive region-wide blackouts, a thing of the past? Could we end up with these super resilient localized power networks instead? Something to definitely consider as you, plug things in today.